Hi, I'm Avis Nizamani. I'm excited to present our work, Dynamic Neural Surfaces for Elastic 4D Shape Representation and Analysis. This is a collaboration between Murdoch University, the University of Western Australia, and Florida State University. 4D surfaces are composed of 3D subjects that deform over time as a result of internal and external factors. For instance, human faces deform while talking or performing facial expression, and human body shapes deform as a result of actions or motions. Our goal is to develop a mathematical framework that is able to spatiotemporally register the set of 4D surfaces using statistical shape models. On the left, we show a set of unregistered 4D surfaces as input and compute their mean on the bottom. On the right, we show 4D surfaces after spatiotemporal registration and their mean on the bottom. We now present our method of statistical analysis. We learn a continuous representation of static surface F1 by overfitting a multi-layer perceptron. The MLP maps the point on the sphere S to a 3D point on the surface F. We use a residual connection to learn coarse and fine geometric details. Given two static neural surfaces F1 and F2, which are originally unregistered, we spatially register F2 onto F1 by finding a spatial diffeomorphism gamma and rotation O that brings F2 as close as possible to F1. This is an optimization problem where DC should measure the amount of bending and stretching one needs to apply to F2 to align it onto F1. Such a nonlinear metric is complex to work with. Thus, we map the surfaces to the space of square root normal fields. In this space, the elastic metric becomes an L2 metric. Once the surfaces are spatially registered, we add the temporal dimension to create dynamic neural surfaces. Now, given two spatially registered surfaces F1 and F2, their temporal registration can be formulated as that of finding a time warping function zeta that warps the time dimension to temporally bring F2 as close as possible to F1. This is an optimization problem where D is a measure of closeness and thus D should measure elasticity. However, working directly with the 4D surfaces is computationally expensive. To address this, we map the 4D surfaces to the space of square root velocity fields, where the partial elastic metric that measures bending and stretching of curves becomes an L2 metric in the SRVF space. Now, given spatiotemporally registered 4D surfaces, we can perform statistical analysis like computing 4D geodesic and mean. The geodesic can be defined as the shortest path with respect to the elastic metric. Since the SRVF space is Euclidean, then the geodesic path lambda between Q1 and Q2 is a straight line. Similarly, the 4D mean, also called Karcher mean, of a set of 4D surfaces is a 4D surface that is the closest to all the input 4D surfaces after their spatiotemporal co-registration. Results. We show some results demonstrating the representation quality of the proposed dynamic neural surface. In the form of a heat map, we show the error between the original and neural surface. As one can see, the errors are less than 0.01. These are some results of spatiotemporal registration. On the left, we show the results before registration, and on the right, after registration. Now we show the results of 4D geodesic. On the left are before registration and on the right are after registration. These are the results of 4D mean. On the left are before registration and on the right are after registration. For more details, please scan the QR code or visit our website.